So building from what we were talking about yesterday, we started to work with systems of equations, and we're going to work more with matrices beyond row echelon form and reduced row echelon form. Let's warm up with some examples based on our techniques we were working with yesterday. So we saw how matrix algebra, and in particular Gauss-Jordan elimination, helps us solve systems of equations. We will get into more of how to manipulate matrices and some of the other math behind matrices that will help us throughout linear algebra. And so, of course, we just want to solve a system of linear equations. And the way we do that is by creating an augmented matrix. At least this is our second technique. Our first technique was maybe using some substitutions or just doing elementary operations on the equations themselves. We've learned that doing elementary operations on the equations is the same as doing elementary operations on the augmented matrix. So we can save ourselves a little bit of writing, a little bit of work to manipulate these guys. So let's see. Let's try to start with equation 1. And let's just multiply it by a half. So we will have 1, 2, minus 3, and then, sorry, minus 3 halves and 1 half. And then these other equations are not going to be nice. So it looks like our numbers we are given is not terribly simple. So I'm going to start doing some of these steps sort of in conjunction to save ourselves some writing, so I don't have to write this out every time, just to save some time. So if I do 1 half times row 1, this is our new row 1. And then what we want to do is use row 1, since I now have a 1 in this position. We want to use that to get rid of the 1s, or get rid of the numbers below that. So we want this to be 0 and this to be 0. So we will have minus 5 times that new row 1 plus row 2. And so what's that going to give us? It'll give us a 0 here. And so we'll have minus 10 plus 10 will give us a 0 there. Now our algebra is going to get a little messy. So we've got, what is that going to be? 15 halves minus 7. So 7 is 14 halves. So 15 halves positive minus 7 is going to give us that 1 half. And then in our last term over here, we will have minus 5 halves minus 2. So 2 is 4 halves. That should give us minus 9 halves for that middle row. And then our third row, we want to do minus 3 row 1 plus row 3. And so we'll get a 0 here. We'll have minus 6 plus 6 will give us a 0 again. And then we've got, let's see, minus 3 row 1. So that'll give us 9 halves plus 5, which is 10 halves, giving us 19 halves. And then in our constant, we will have minus 3 halves plus 9, which will give us 15 halves. So we've got our row echelon form started here. Unfortunately, what's going to happen, so let's do 2 times row 2, because we want a 1 in the leading position. And then we can also do 2 times row 3, just to get rid of those denominators. Maybe make the numbers a little bit easier for ourselves. But now what's going to happen, we've got row echelon form for the first and second row, but this third row, if we do now 19 times row 2 plus row 3, and let's make it a negative 19 so that those cancel. We'll have a 0, 0, 0. And then what's this other one going to be? It looks like a mess. So negative 19 times row 2 will give us 9 times 19 positive plus 15. So whatever that is, 171 plus 15, so 186. So what's going to happen here? This ends up being a problem. So we mentioned yesterday that the rank of the system is essentially going to be the number of rows with leading coefficients 1. So here we have, when we put it in row echelon form, the number of rows with a leading coefficient of 1 is going to be 2. And again, we only want to consider these leading coefficients in the part of the matrix that represents our coefficients in our coefficient matrix. In the constant terms, those we kind of want to keep slightly separate. That's why we keep that bar there. And so right now, if we were to convert this back into our equations, what will we get? We'd have a system of equations that says x plus 2y minus 3/2 z equals 1/2. We have an equation that says z is equal to negative 9. And then this last equation says 0 equals 186. And so when we see a statement like this, no solution. So that statement, anytime we see a statement that doesn't make sense, 0 equals 186, no solution. So if we end up with a row without a leading coefficient, without a 1 in it, could be no solutions or it could be infinite solutions. So anytime we have like a 0, or excuse me, there's no 1, so it's going to be all zeros, but then a constant that's non-zero, going to be no solution. Let's do one more example. And this other example should have infinite solutions. So we've got 3x minus y minus 5z equals 9, y minus 10z equals 0, and minus 2x plus y equals negative 6. So we write our augmented matrix. And then let's see. So we need our leading coefficient to be 1 in the first equation. I'm going to actually switch these two equations. So minus 2, 1, 0, minus 6. I'm going to keep this equation here, 1, 0, minus 10, 0. And then move the top equation down to the bottom. The reason I'm doing that is because when the leading coefficient isn't 1, really what you can only do, you want to just take one of the equations and divide out by whatever that leading coefficient is. So this minus 2. And if we had done it with this equation, we'd have a third in the denominator. So it would just be harder computations. So this was row 1. We're going to flip with row 3. And then now we're just going to do 1/2 row 1. Let's do, sorry, negative 1/2 row 1. So we'll have 1 minus 1/2, 0, and 3. So that worked out not too bad. Only a single fraction in that one. Column 2, let's keep the same since we already have a 0 leading on that guy. And then the 1 already in the y position. And then let's do now this column, or excuse me, that row, minus 3 times row 1 plus row 3. So that'll give us a 0 here. We're going to have positive 3/2 minus 1 will give us a 1/2. And then let's see, we've got minus 3 row 1 plus row 3. We'll still have a minus 5 here. And then minus 3 row 1 plus row 3 will give us 0. So we've got a minus 3 times that 3 plus that 9 in row 3. And now we've got the first 2 rows in row echelon form, 1 and a 1. So let's go ahead and get rid of this 1/2. So what we want to do now is let's do minus 1/2 row 2 plus the new row 3. First row is not going to change. Second row is not going to change. The third row, so minus 1/2 plus that 1/2 will give us 0. What's minus 1/2 of 10? It's going to give us positive 5 plus 5 will give us 0. And then, of course, we'll have a 0 plus a 0 in that last column. And so what do we see? We have a row of all zeros. And this is fine. This is going to imply that we have infinity solutions. And why is that? If we rewrite our equations, we have x minus 1/2 y equals 3. We've got y minus 10z equals 0. And then that last equation just says 0 equals 0, which is perfectly fine. It's a valid statement. And so what is our solution? If you've had Calc 3, hopefully this isn't too bad. If not, well, I'll try to go through it here at least once. Essentially what you can kind of think of as we have 2 equations. In 3D. Let's write it as 3 dimensions. Equations you want to think of as restrictions. Every equation we have restricts our dimension. So we've reduced our system down now to only 2 restriction equations, 2 restrictions on our variables, on our set of 3 variables, meaning we have one degree of freedom. Or you can also call that 1 parameter. And so what you can do is generically, you can pick whatever variable doesn't end up showing which is, of course, usually always going to be z up to flipping them. Just to declare that as a parameter. Usually we use t or s as a parameter. We think of it as time moving forward. So how is z going to change in time? Z is just going to change linearly in time, directly with time. And if you really want, you can write it as a function. So z of t is t. And then by our equations, we know that y now is a function of t minus 10 z should be 0. So our function for y of t, well, z of t is just t. So y of t equals 10. And then now we can do the same thing for x. So x minus 1/2 y of t was 10t is equal to 3. So we get x is equal to 3 plus 5t. So in other words, what you can do is write our parametric equation for our position, or the solution is going to be 3 plus 5t, 10t, and t. Is one way to write it. We can also write it as column vectors. So we've got 5, 10, and 1, all times t, plus our starting values of 3, 0, and 0. Oops. So we'll formalize this a little bit more today, talking about column vectors and matrices. Any questions on that, on either of those? The other thing you can do is if this notation here is a little confusing to you, for now, having these three equations is good enough. We have a parameterization of each of our coordinates, and that does parameterize a line in 3 dimensions.
So this should only exclusively be used when we have infinite solutions, or when we have a situation that implies infinite solutions?
Okay. So let's talk about matrices and matrix algebra. I'm going to skip some of the stuff that the book does. We simply just don't have time. And if we have time at the end of lecture, maybe we'll go back through it and introduce block notation and block form of matrices. It actually makes things simpler in some sense and kind of shows the linearity in some sense. It's a different type of linearity of matrix multiplication. But I don't know. I don't think it's terribly essential at this point, and we don't have a lot of time. So let's just talk about matrix algebra. So again, a matrix is just an array of numbers in a square. And so we call this, usually denote matrices by capital letters A, which we can write out the entire block, or we often denote by this, where we have our bi index, our double index, I and j, and we just put that in sort of a bracket by itself, and then we usually indicate the range on the indices. So it's always row, column. So I is our rows going downward, j is our columns moving to the right. And then we call this an m by n matrix. So first thing we can do with matrices is scalar multiplication. So scalar multiplication just means for any real number, let's call it a t in R. So again, this just means it's a real number. We can have t times a is just the same thing as the matrix, every element of the matrix being multiplied by t. Sorry, I don't have chat open. Where you guys have questions? I cannot hear you guys. Have you guys been saying anything? Let me pause real quick. All right. So matrix algebra, scalar multiplication, we just multiply the scalar by every value. So I don't want to rewrite it out in terms of a big general matrix. Basic examples, if we have A is, let's say 1, 2, 3, 0, -1, and 1, 0, 0, then we can compute 2 times A just by multiplying all the values. So 2, 4, 6, 0, -2, -2, and then 2, 0, 0. Then we have addition and subtraction. So of course, subtraction we can think of simply by multiplying the matrix by -1 and then adding. So we need matrices of the same size. So both of the index, I use the same indices for both A and B, primarily because they go between the same range. And then if we want to add two matrices, of course, we just add term by term in the corresponding positions. So for example, if A is -3, 0, 1, and 2, and B is 5, 7, -3, and -5, then A plus B, top left position, we just add, we'll get 2. And then here we'll get 7. Here we'll get -2. And then here we'll get -3. So properties. We have all of the, pretty much all of the typical properties hold. I mean, A plus B. Let me see if I can list them all. I don't have them all written out in my notes, so hopefully I'll be able to remember them all. Of course, addition is going to be associative. Doesn't matter what order you add in. Likewise, we're going to have commutativity of scalar multiplication. We've got reflexive. We've got our distributive law. Likewise, the distributive law for sums of scalars. So we should say A and B are m by n matrices. S and T are real numbers. So associative, distributive, all the other important properties. So essentially any of the properties between multiplication and addition that we have for real numbers, you can essentially deduce those equivalent properties for matrices just by how they're defined. Okay, so let's talk about matrix multiplication and how to multiply matrices. So the way the book does this, they start off and they essentially do it with block notation on their columns, which isn't bad, but it's not the way you typically compute it. So I am just going to write out an example. Hopefully you guys have seen this somewhere in your education. I would be sad if you haven't seen it somewhere in middle school or high school. But let's say we have a matrix. A is 1, 0, 2, and 3 minus 1, 0. And we've got B is, let's say, minus 1, 3, 0, minus 2, minus 4, and 0. So A is a 2 by 3 matrix. B is a 3 by 2 matrix. And so what is going to happen when we do matrix multiplication is if we have A times B, we've got a 2 by 3 times a 3 by 2 matrix. So note these numbers have to be the same. And how we're going to multiply them is you're going to list them next to each other. And what you want to do is to start with, so let me try to annotate this as we go. So this position is 1, 1, right? First row, first column. Means where you're going to take the first row times the first column. Meaning I take 1 times -1, 0 times 0, and then 2 times 4, -4, and then we add those up. So what goes in this position here is going to be 1 times -1 plus 0 times 0 plus 2 times 4. Everyone see how that works?
Shouldn't it be 2 times -4?
-4, yes, thank you. So we computed that first position. We're going to get -1, -8. So we'll have -9 in that first position. And now we can move on to the other positions. So for example, in this next position, position is the first row, second column. So we're still going to have the first row times the second column. And so we've got 1 times 3 plus 0 times -2 plus 2 times 0. Then we can move on to this position, which is now second row, first column. So we start with our second row on the first matrix, first column, and then we multiply in the corresponding positions. So the first one is 3 times -1. -1 times 0, and then plus 0 times -4. And then our last one so we've got -9. Looks like we'll have 3 in that second position. Then we've got, let's see, -3 in that position. And now our last one, position 2, 2. So we do second row, second column. We will have 9 plus 2 plus 0. Any questions on that? So just remember that algorithm. Let's write it down formally. The other thing to note, actually, before we move on, is the inside numbers. So A is a 2 by 3, B is a 3 by 2. Our result is going to be 2 by 2. So it's kind of like the inside numbers dictate the multiplication. The outside numbers dictate the remaining size after the multiplication. Formally, so for A equal to Aij, where, let's say A equals Aij, B is equal to Bjk, I is between 1 to m, j is between 1 to n, and k is between 1 to p. So in other words, A is in m by n, and then B is in n by p. Then the product is going to look like this. Here, actually, let's do it. We've got to do it with a by sum or try sum, really. So AB is going to be a matrix C, IK, where CIK is going to be the sum of Aij times Bjk, and the sum is going to be over J. This is just a formal mathematical way of describing the exact process we just did. So the IK entry, the IK position of the new matrix, we take the ith row of A, multiply it by the kth column of B, and then we add up the different positions. So going along the row of A, we add up, we take the different columns, the different entries in each column, and multiply it up by that corresponding entry within the different rows for B. Any questions on that? Okay, so some special matrices. So a 1 by n matrix here, let's put a declarative equals. We call a row vector. So of course, this is just going to be essentially like A1, 1, A1, 2, up to A1, n. We commonly, if we're just working with a vector of one dimensions, we won't put both of the coordinates since there's only one row. So more commonly, we will write it as A1, A2, up to AN. Conversely, if we have an n by 1 matrix, that's our column vector. So A1, 1, A2, 1, dot, up to AN 1. And of course, same situation. We commonly just write one of the indices. And of course, it's clear by the direction we draw it whether those indices are row or columns. So we can have matrices, matrix multiplication on column vectors. We call it matrix action. And when I say matrix action, just think of it as multiplication at the moment. We'll have better ways to describe it once we get to chapter 4 and 5, when we start to talk about linear transformations on column vectors. So if we have, let's see, let me write some numbers, 1, 0, 1, minus 2, 1, 0, and let's keep it at that. Let's keep it at 2 by 3. So again, maybe if you want to put some notes, we have a 2 by 3, which means it has to act on the column vector of size 3. What is that going to give us? So in our first position, we will have first row, only column. So 1 times 7 plus 1 times 5 will give us 12. And then in the second position, we will have minus 2 times 7 minus 4, so minus 18. And so only 2 positions there. We will see later on in the semester that this represents, that this matrix will represent what's called a linear transformation, which is a transformation of 3-dimensional vectors into a 2-dimensional space. And so in some sense, we can think of this vector 7 minus 4, 5 being sent to this vector 12 minus 18 under the action of this matrix. We'll get to that eventually. For now, really what we want to do is to just be able to represent our systems of equations now in terms of an action of a matrix on our standard variables. So in other words, let's just show this by example. If we have x minus y plus 2z equals 4, we've got 3x plus 2y minus 2z equals negative 1, 5x plus 2y minus 6z equals 7. The technique we know at the moment is to represent this as an augmented matrix and then do row operations. We're going to start to get into some other techniques. And so how can we do that? We can now split it into 2 separate matrices. So we've introduced our coefficient matrix. So what we're going to do is take all the coefficients of our variables and we'll put those in one matrix. I'm sorry, ignore that plus. You don't want to include the pluses. So this is our coefficient matrix. On the other side, we are going to have our constant matrix. And what we can put here now is actually just our matrix of variables. So we can actually represent systems of equations in a much more nicely and concise way with this matrix multiplication method. So check this. I'll leave this to you guys to check on your own, that if we now do a matrix multiplication on this column vector containing our independent variables, then we will recover this system of equations. I guess we should note, if it isn't kind of clear from the context, that two matrices, A equals B, if they're the same size, and the coefficients, or excuse me, the entries are equivalent at corresponding positions. So all of the entries are the same. So this is essentially how we're going to get this equality. This matrix here times our matrix of independent variables. What is that going to give us? That will give us a new matrix, or a column vector, just as we saw over here. A matrix acting on a column vector will give us a new column vector. So this new column vector that we get here is actually going to be a matrix of these equations. Should recover this in matrix form, now with all these equations listed in each entry of a column vector. And then that column vector is going to be equal to this column vector. And then, of course, two column vectors are going to be equal if each position is equal. And that will give us the recovery of our system of equations. Any questions? So example problem statement for this, it might say something like, write the system of equations using matrices, or something to that effect. And then you would end up with something like this. Okay, so we've got about 30 minutes. Let's see, what else do we need to cover? So we need to talk about transpose and inverses. So the next natural place to go is inverses. We do need to cover transposes, though. And then I think elementary matrices we will get into tomorrow. Let's do one other note. We're not going to have time to explain this before moving on to inverses. So check our previous example that we started with for matrix multiplication. We had two matrices here, A and B. Now we did A times B. We went through the algorithm of how to multiply those matrices and some intuition behind, what we should expect to get. We need the columns of A, the number of columns, to be equal to the number of rows of B, and then the resulting product is going to be it's going to have the same number of rows as A and the same number of columns as B. So the result here was a 2 by 2. If we switch those, we're going to get something different. So A times B is not necessarily B times A. This is what we call non-commutative. Multiplication. And as an exercise, compute B times A from the previous example. Even without doing the multiplication, I know it's going to be different. And why do I know it's going to be different? Because B, sorry, let me make sure I get the order right on here. B was a 3 by 2, and A was a 2 by 3, which means the result is going to be 3 by 3. So when we did A times B, we got a 2 by 2. If we do B times A, we're going to get a 3 by 3. The other important note, of course, is for any matrices, may not be possible. So the other thing that could happen, right, if B was a 4 by 2 and A was a 2 by 3, well, we can multiply in one direction, but if I flip the order, we cannot even compute it. And of course, in general, if our matrices aren't of the correct sizes, we cannot multiply them. So there's some properties of multiplication. I'll reference you guys to the book and make sure you guys know them. Let me pull it up real quick and see if I can find what page it's on to at least refer you guys. It is all the typical properties of multiplication, like the distributive law, the associative law, multiplication by identities and things like that. Let me see if I can find it where the book has them listed. Here we go. Yeah. I guess I can draw them out real quick. I'll leave you guys to check those. They're not very hard. And again, most of it follows from scalar multiplication from the properties of real numbers, as well as the definition that we just introduced for how we multiply matrices. So this is proposition 2.25 on page 68 of the book. This is just properties of multiplication. You've got A times RB plus SC. Capital letters are matrices. Lowercase letters are scalars. And so for scalar multiplication, it doesn't matter which side of the matrix you multiply on. But I will warn you guys, be careful with matrix multiplication, right? If they are of the correct sizes and we can multiply them, there is a distributive law, but you have to make sure that that C stays on the right when we distribute over addition. Multiplication, when the sizes are correct, is also associative, though. So take a look at those. Work them out for yourselves, or at least gain an intuition. Do an example or two, and it should probably be enough to build your intuition and understand why all of these statements are correct. Okay, let's move on to inverses. I'm going to put a hold on transposes for now. Inverses, I think, are more important because we want to extend our methods of problem solving for the systems of linear equations. So an inverse is the multiplicative identity that we need. So let's start off with special matrices. We often like square matrices. So n by n, we call square matrices. We can have the zero matrix. which is a square matrix of size n by n. So it's always a square matrix. Well, it's usually clear from the context what the size is. So if we write 0, so for example, if we have some matrix A and I write A times 0, whatever the size of matrix A is, if it's 4 by 5, then if I say times 0, it's implied that this 0 is a 5 by 5 matrix of all size 0. And you can check that if I have a matrix, no matter what the entries are, if I multiply it by a matrix with all zeros, we are going to get a 0 matrix back. And then we have constant matrix, which is just a matrix consisting of all the same number. So all the entries are the same. Usually you can think of it as t times, sometimes we denote it as 1. And maybe make it like a bold 1. So a matrix of all ones times any constant, any scalar will give you a matrix of all that scalar in every entry. And then our last, and probably the most important out of all these, is our identity matrix. So the identity matrix is a square matrix with ones on the diagonal and zeros elsewhere. Mathematically, how do we represent this? So we often call our identity matrix I, and sometimes we'll put a subscript down there. So if I say I sub n, it just means an n by n identity matrix, where it's given by this delta ij function, which is called our Kronecker delta. So 1 if I equals j, 0 if they're not equal to. So Kronecker delta function. So if you're in physics, you'll probably see this. It'll come up time and again. And of course, if we were to draw out this matrix, we often write it something like this, implying that we have ones going on the diagonal, zeros everywhere else. Now, what is special about the identity matrix? Sorry, did everyone finish writing, taking notes and everything? Okay. The identity matrix is nice because so I'm going to introduce some notation just so it'll help me not have to write out so much. Let's just introduce this notation. This means A is, so this element you can read as is. A is an element of this set, or A is, and M by N matrix. So the capital M stands for matrix. The little m by n tells us the dimensions. So that way I don't have to keep reading that statement out. So for an m by n matrix and our identity, so I is always going to represent the identity. So in, which is just the identity element in square matrices, so n by n, im is the identity of just a different size. So same form, one's along the diagonal, zeros elsewhere. We have so a times I to the n is equal to a, and I to the m, or im times a, is also equal to a. In other words, multiplying by the identity matrix gives us back the exact same matrix. And I'll leave that as an exercise. Pick some matrix, pick your favorite matrix of whatever size, multiply it by an identity, either on the right or the left, and check to see that it will compute and give you back the same matrix you started with. So these identity matrices operate like the number 1 for real numbers. Anything times 1 is that number, right? 1 times anything is that anything. Same thing with matrices. The identity times any matrix, it gives us back that same matrix. This is our multiplicative identity. And so what we want to do is try our best to come up with division. So we've been talking about multiplication. The natural question is, can we divide matrices? So I kind of mentioned it with addition. If I want to undo addition, we can always subtract, right? And how do we subtract matrices? Well, I didn't formally write out how to do it, but we did formally write out how to do scalar multiplication and addition. So I could always take a matrix, multiply by -1, and then add it to another matrix. That would be equivalent of subtraction with matrices. What about division? So what is division? How do we come up with division? Really what division is a notion of introducing fractions in our real numbers. So starting with, say, the integers, we have to then expand the set of integers to rational numbers. And for real numbers, really what division is, if we have s divided by t, it's really s times what we call the reciprocal of t, or s times t inverse. In other words, the heart of division is really looking for a multiplicative inverse. Right? What is this t to the -1? It has a property where if I take t times t inverse, or if I flip the order around, t inverse times t, we get back our identity, our multiplicative identity for the real numbers. So for matrices, we are looking for, so let's say, let's change it, let's say for a matrix, capital A, we are looking for another matrix that we will call A inverse, such that A times A inverse is the identity, and A inverse times A is also the identity. So note, this forces any matrix that has an inverse to be a square matrix. So same rows, same number of rows and columns. Mainly because we want to be able to multiply on the right and left. We want to be able to switch the order. And as we kind of saw with multiplication, we can't necessarily switch the order of multiplication. Sometimes it doesn't work. And if we can, and the result, I know that this guy is a square matrix. So if I know our result is always a square matrix and we can flip the order of multiplication to get the same size of a square matrix, it forces both A and A inverse to be square matrices. So another point, check that on your own. Let's go through the process of how to find an inverse. And then maybe we will see how we can then use inverses. And let me look for an example I've had. Okay. So let's say we have a matrix A. And our problem just says to find the inverse if it exists. So this is going to be one of the problems, just in the sense that we cannot multiply every matrix together. Well, we already know that, as I mentioned before, a matrix that has an inverse has to be square. So there's a lot of matrices, namely nothing that's square, anything that's not square, that will never have inverses. It also turns out that even if a matrix is square, it may not have an inverse. So there's only a certain class of matrices that will have an inverse. Not all of them will. And so how do we check whether it has an inverse? Our process. We want to make an augmented matrix except what we want to do, instead of having like one column of constants over here, we're simply going to put an identity matrix to the right. So we're going to kind of create a mirror dimension, so a 3 by 3 identity matrix on the right. And you should be kind of gathering, well, the nice thing about these identity matrices is it is a reduced row echelon form matrix, right? So yesterday when we were looking at reduced row echelon form, we saw how if we're trying to solve a system of equations and just had an augmented matrix, we want to put this left side in reduced row echelon form and kind of see what's resulting on the right, and that will give us a nice solution to our system of equations. So we were essentially going to do the same thing. And if we put this right side in reduced row echelon, or excuse me, put this left side in reduced row echelon form, ideally what we want is the identity matrix. We want to get ones in our leading entries and have exactly 1, 1 for each column. And so when we perform these reduced row echelon, or these operations to get reduced row echelon form on the left, we're going to perform the same operations on the right, and then that matrix on the right will give us the inverse. So let's go through that. Okay, so what's our easiest way to start with? We're going to keep our first row the same, since we already have a 1 leading there. Let's multiply the first row by a -1, add it to the second. So we'll get a 0 here, -2, a 0. And then here I'm going to have negative times this guy plus this guy. So excuse me, we've got a -1 here, a 1 here, and a 0. Row 3 did not change, but we can go ahead and perform this operation as well. So since we want to get rid of this leading 3 first, we'll do -3 times the first row plus this guy. So we'll get a 0. We'll have -6 plus 1 gives us -5. -6 minus 1, -7. We will have, let's see, -3, and then 0, and that 1 will stay. So you may want to write out your work. I would make sure you write out your steps, especially exams going to have examples like this. There's probably going to be a question where you have to find an inverse if it exists. So for me to follow your guys' work, try to write out your steps and include some sort of notation best you can. So something like -1 plus minus row 1 plus row 2, and then -3 row 1 plus row 3 will give us that step. So I'm fine with you guys doing multiple steps in one like we're doing here, just to save yourself some writing. But try to indicate it as best you can. Okay, so now we want to essentially get rid of that 2 here. So we've got 1, 2, 2, 1, 0, 0. We are going to multiply this guy by 1/2, so -1/2. So we'll have a 1 here, a 0 here. That will become a +1/2. This will become a -1/2. And this one is 0. So this was just -1/2 row 2. And now we can use that row 2 to eliminate these terms in row 3. So what do we want to do? -5 row 2 plus row 3. And careful with stuff like this. I did some of these steps in the opening examples we did, and now this -5 times row 2 is this row 2 after we've modified it. And that should be good enough notation if I see you work out something like that to indicate for me to know what you're doing here. But just be careful with the constants. All this arithmetic, it's the other thing I want to grade you guys on is, do you understand the process? If you make one addition error or one minus sign error, all could be lost, and I don't want to like burn you guys on problems. No one should be burned on that, especially at this level. Making a small arithmetic error isn't the biggest of deals. I just want to make sure you guys understand the process and how to do it. Okay, so we've got -5 times this guy plus, and it should be +5, excuse me. So +5 times this guy plus this guy. So that'll give us a 0 here, and then this number is going to be ridiculous. No, yeah, just -7 still. That's not too bad. And then we've got, let's see, -5 or 5 times 1/2 plus -3. So 5 halves minus 6 halves gives us -1/2. And then we've got -5 halves plus 0. And then we've got 0 plus 1. And please, if I make any sort of algebraic arithmetic mistakes, please speak up, let me know, so that we don't carry them through. Okay, so let's rewrite that real quick. And now what do we want to do? Looks like we need to divide by 7, divide by -7, which is a pain. So 0, 0, 1. We've got 1 over 14, and then 5 over 14. And dividing by 7, -7, we'll have a -1/7 there. So let's do that one first. Row 2, we can keep the same. So nicely enough, we don't have to mess with this guy anymore. So we've got 0, 1, 0 in row 2. It's row 1 that we're going to have to mess with. So let's go ahead and do, which one do you want to do first? Since we just modified row 3, I'll indicate that my steps are going upward. So we did this first. Now we're going to modify row 1 and do -2 times row 3 plus row 1. So we've got 1, 0, and now I'm taking -2 times this row. So -2 plus 2 will give us that 0 there. Sorry, this guy's still 2. Let's do one more step after this. And then what's going to remain in here? So we will have 1 plus 1/7 minus 1/7. So 6/7. We will have -2 times that guy. So -10 over 7 plus 0. So -10 over 7. And then now 2 times that guy. Wait, did I do that right? No, -5 over 7. Sorry, I'm doing the -2 twice. Like I'm saying, doing all this arithmetic, it's easy for your brain to get a little fried and just miss one little mistake. Right, because we have -2, so it'll be -5 over 7 plus the 0. And our last one will have 2/7 plus 0. So 2/7. So far, not too terrible. And then now our last step, we need -2 row 2 plus row 1. And this one might be a bit of computation. So let's write out everything we have. And then we need -2 times this row plus the first row. So it'll give us a 1, 0, 0. That's our identity on the left. And then now how do we mess with these guys? So we will have -2 times 1/2 gives us 1. -1 plus 6/7 gives us -1/7. -2 times -1/2 gives us a +1 plus 5/7 gives us 2/7. And then our last one, -2 times 0 plus 2/7 gives us a +2/7 again. So this guy should be A inverse. Check that. So the best way to check your work is, well, we didn't know. I mean, I could have made some algebra mistakes, some arithmetic mistakes there. I'm not sure if anyone caught them, but we want to check that now if I multiply A times A inverse, we get the identity. So homework, check that on your own. Practice your matrix multiplication. See if we did the computations right here. And if not, go back through the process and try to figure out where we made our mistakes. Any questions? Okay, so as is kind of typical with these types of semesters and how much stuff we need to cover, we're going to have to start skipping a few things. Tomorrow, I want to start off with an example of how we can use inverses now and how we can use inverses to solve a system of equations quite easily. So for you guys that are computer scientists, this is actually like a fairly easy algorithm to implement, because you can, one, program a computer to compute inverses directly for you using matrices. And now if you're given systems of equations, you could then solve them pretty quickly by computing the inverse quickly and then doing some quick matrix multiplication. By hand, it's going to take us a little bit. As we've seen, some of these steps, they can get a little tedious, especially with the fractions. But it is an important method for solving systems of equations. We'll have to also talk about transposes. Transposes, they're important. I don't know how terribly important they are for this class, though. So we'll mention them, and maybe they might show up later in the semester of what important properties they have. But the key thing is we want to be able to use inverses to solve a system of equations. And then we actually want to move on and start talking about elementary matrices and what is called LU factorization.